as you'll see as we go through here, we're going to say, this is going to be, in a sense, between today and some of the later lectures, perhaps the most boring repetitive piece, because I'm going to say some of the same things over and over and over again. So it might be a hint that they're good things to know for the final. It's also a hint because they are the things that we just use over and over and over in physics. And as we learned our lesson with complex numbers, apparently I can't repeat an idea enough. So let's, having done that in the plane, let's switch gears slightly and focus in on the yes? Oh, sure. Let's focus in on a really key basic physics idea here. And we are now going to spend, having just said and established that divergence is flux and curl is circulation in the plane, we're going to go through it again here, and then we'll go through it again when we do integral theorems, and we're going to go through it again when we talk about some other physics things. But the fundamental physics idea, the reason we learn about curl and divergence is because they fundamentally tell us about physics. They're obviously very useful, interesting vector derivatives, right? If you wanted to come up with the vector derivative, you know, these are the two obvious things to do. Define a vector like we did for the gradient, which we had a natural reason to define, and then just use dot and cross product, because those are the two ways to multiply vectors. So it turns out to be really nice that they have fundamental physics meanings. And the first core physics idea is flux. And this shows up in fluids, where it's kind of obvious. Fluids flow, they have a flux. It shows up in thermal situations where you have heat fluxes. It shows up in electromagnetism where you have electric and magnetic fluxes. It basically shows up anytime you have a vector. We have momentum flux, we have mass flux. So it even shows up when you have scalars. But that mass flux is when you have a velocity for the mass. So that's a vector showing up. So almost any vector, we will talk about the flux. And intuitively, the question we like to ask, and I didn't bring any demos, sorry, right? If you are in Las Vegas, and nobody does it anymore because they don't spit out coins, but if this machine were to still spit out coins, okay, and the coins are coming out of the machine, and you have your bucket, how do you hold the bucket to maximally catch coins? Perpendicular to the flow of the coins. We don't tilt our bucket at an angle, right? We have, I like to put it in very concrete terms. Think about water, however you want, right? The key idea to flux is the perpendicular surface. So if I have here a n hat perpendicular to my area, and we have some vector field v that's flowing out, and if at some point my surface is cut at an angle to the direction of v, the only piece that matters for the flux is, you can either think of it as the component of v perpendicular to the surface, or the part of the surface parallel to v. The language gets a little tricky because, of course, if I have a surface, I define the normal to the surface. That's the thing I care about. And so what I want to maximize flux is v parallel to n, or v perpendicular to the surface. So if you hear someone say, I want the velocity parallel to the surface, they're probably implying parallel to the normal to the surface, parallel to the surface vector, parallel to the area vector. You can get a little sloppy in the language and sometimes mix these. And that's just kind of a warning. But the fundamental idea, right, is if I have v at some angle, it's only the component v perpendicular that matters. And so what we want to do is our favorite what? Because we're going to do what? The P word. We're going to project. You are allowed to use the P word in physics. Right? So we do v dot n hat. And it all comes back. Right? I told you way back when we first did projection, it's one of the most fundamental mathematical concepts in physics. So we're going to project. And that gives us basically the flux. And the way we actually get the total flux is we have to have the amount coming through times the area it's going through. So we actually have to include the magnitude of the area, which maybe it's d sigma. There's just lots of notations. So you'll see things v dot n d sigma. So that just puts the n hat separate from the magnitude. You'll see v dot n dA. You'll see v dot dA with a vector sign. You'll see v dot ds with a vector sign. And I can even do v dot n ds. So ds, dA, and d sigma are the most common indications of areas and surfaces. Just depends on the application. And the key idea, which we're going to delay the proof of, is the following. We just take our general principle. So this is over a closed surface. So a closed surface is the boundary for what? A closed surface bounds what? A volume. So this is the boundary of a volume. And so since this is the boundary, what goes in the volume integral?
The scalar function.
It's going to be scalar, but it's going to be, if this is the function, what goes with the volume? The derivative. And since this is one that's easy. Volumes are a scalar. This is a scalar. The only thing I can put here is the divergence. I can't put the curl. There's no way to get the curl in here and make it work. So this is the easy one to remember. And now we see, we had said physically divergence tells us about flux. And now we see that fundamental connection really comes from our underlying integral equations, right? Is that this is clearly flux. This is just the definition of it, right? We define flux as stuff coming through a surface. And an integral adds up little pieces. So notice all of our big ideas are coming in here. Integrals are adding up things. We add up all the little individual flux pieces. That gives us the total flux. And then we see that's related by our integral relation. That means divergences in the volume must be related to the total flux out of the surface. And that's the connection there. Now, a couple things to notice. The conventions, closed surfaces are easy because we take the normal to be out. And if I have a closed surface, out is well defined. And so flux out is positive. And flux in is negative because of that definition. So you got to watch for conventions, but that's the most common convention. I can, of course, define it the other way if I want. If I have a flat surface, then it's arbitrary which side is the normal. I mean, not a flat surface, an open surface. It's kind of arbitrary which side is the normal. So positive and negative flux you have to define by convention. Now, one thing I like to keep in mind is the following picture that really helps. So imagine I have a completely uniform field V. Is the divergence 0 or non-zero? Why 0?
In is equal to out.
Well, everything in is equal to everything out, but also if I told you this is completely uniform, what does it mean?
There's no change.
Yeah, it's constant. And if I take the derivative of a constant, I get 0. So this is the most trivial, uniform, no divergence field. And any surface I draw, whatever comes in goes out. And so the flux is 0. So this is the pretty easy flux 0 case. Now imagine the other case that's standard to picture is a point source of stuff. Now what's the flux? Well, is the flux non-zero or zero?
Non-zero.
It has to be non-zero. There's no way to cancel the stuff coming out because there is only stuff out. And so now the divergence is non-zero. And what field does this fundamentally look like? A point charge. And the divergence of a point charge is not zero. Right? That's, del dot V equals 4 pi rho. So we just derived one of Maxwell's equations by just thinking. Okay? So this is key. And likewise, if it's a sink, if everything's flowing into it, again, you would get a net flux. So those are two good pictures to keep in mind.